An actuator is a mechanism for moving or controlling something indirectly, instead of by hand. For example, in response to a remote signal, an actuator can open or close valves, raise or lower heavy loads, or reposition dampers, louvers, or doors. Automatic control systems use a variety of actuators to regulate plant processes. Actuators usually operate the final control element of a process. For example, this actuator can be used on a flow control valve. Other parts of a control system serve to provide the actuator with a signal, but it's the actuator that performs the control action. In almost any process control system, actuators provide a vital link to the process itself. As an instrumentation and control technician, it'll be your job to adjust and maintain the actuators in your plant. In this unit, we're going to look at some of the background and skills that you'll need for those jobs. We're going to take a look at each of the various types of actuators and see how each type works. We'll also see their construction, their component parts, and their special features. At the end of the unit, we'll be applying some of this background knowledge when we take a look at typical maintenance procedures for actuators and their associated equipment. We'll begin, though, by grouping actuators into general categories, so we can investigate them one at a time. We'll group them according to the type of power source they use: pneumatic, hydraulic, or electric. Let's take a look. This is a pneumatic valve actuator. Like other pneumatic actuators, it uses air pressure as its power source. As the applied air pressure is increased or decreased, mechanical motion is produced. This movement changes the position of a valve, regulating process flow. Pneumatic actuators of this type are widely used in automatic control systems. Hydraulic actuators comprise our second general category. They're powered by the force of liquid under pressure. Hydraulic actuators, when compared to pneumatic actuators of the same size, are usually more powerful and are used to position devices that are heavy or hard to move. Electric actuators are the third category that we'll discuss. In control systems, they can be used to operate valves or dampers by electrical power. In other types of applications, they can be used for heavy jobs, such as opening doors or hoisting loads. All of the three types of actuators we've seen, pneumatic, hydraulic, and electric, can be used as control elements in an automatic control system. Pneumatic actuators, though, are by far the most commonly used type for process control. As an instrument technician, you'll probably be working with pneumatic actuators on a regular basis. So before we investigate them in detail, let's take a little bit of time to see how they fit in with the rest of the typical pneumatic control system. In most pneumatic control systems, signals are transmitted by varying the pressure of control air. Typically, the range of pressure variation is from 3 to 15 psi. These relatively low pressures and slight variations are usually not in themselves sufficient to overcome the resistance created by process flow or mechanical friction. Most actuators need more power to actually move the control element. Positioners are used to control the extra power needed by many pneumatic actuators. In effect, they use the control signal to vary the amount of extra power needed to overcome mechanical resistance. Since positioners are often essential to the operation of pneumatic actuators, we'll be taking a closer look at how they're built and how they work. Before we continue by investigating the first of our three categories of actuators, take some time to review what you've seen so far. When we return, we'll be taking a look at the actuators that you're most likely to work on, pneumatic actuators. In general, any device that uses air pressure to produce a mechanical control action can be classified as a pneumatic actuator. Many different kinds of actuators are used in control systems, but the pneumatic category has wider applications in process control than any other type. The most common of these applications is valve operation. Bear in mind, though, that pneumatic actuators can also be used for many other purposes: lifting loads, positioning components for assembly, operating stamps and presses, opening and closing dampers. The list of possible uses is nearly endless. In almost every industrial facility, though, pneumatic actuators are vital to automated processes. And as an instrumentation and control technician, you're going to have to keep them working right. In this section, we're going to concentrate on several of the most common varieties. We'll see what they look like on the inside, look at their parts, and see how they work. To begin, we'll take a look at this one, a single-acting diaphragm actuator. From this internal view, we can see how this actuator gets its name. Like all diaphragm actuators, this one has a flexible disc called a diaphragm. That's often made of rubber. This is the component that is directly acted upon by air pressure. A metal plate stiffens and supports the diaphragm, helping to maintain its shape. The actuator is classified as single-acting because air pressure acts on only one side of the diaphragm. There's only one port for air to enter. When air pressure is removed, a spring returns the diaphragm to its original position. All of the internal parts serve one purpose: to move the stem of the actuator up and down in response to changes in control air pressure. The device that the actuator moves is attached to the stem. Now that we've seen the parts, let's see how they function together. When a certain amount of air pressure is applied through the port, the diaphragm lifts, compressing the spring and raising the stem. The device that the actuator operates will be moved in proportion to the movement of the stem. If control air pressure is increased further, the diaphragm and stem are lifted to their full extent. By controlling the exact value of control air pressure, a device could be positioned anywhere between its extremes. This characteristic of accurate positioning between extremes is one of the special advantages of diaphragm actuators in general. Single-acting diaphragm actuators, like this one, have another special advantage as well. Here it is. If control air pressure is lost, the spring automatically returns the stem to its original position. For illustration purposes, let's attach a valve to this actuator. In this case, the valve is open when air pressure is applied and the stem is up. If control air is lost, the spring will automatically close the valve. This design is sometimes called air to open, spring to close. This would be the preferred design for a fuel control valve actuator. If control is lost, you want the flow to shut off. Sometimes the opposite is preferred. Notice that the port is now above the diaphragm. With no air pressure applied, the spring holds the stem in the up position. Applying air pressure to the actuator causes the diaphragm to flex, compressing the spring and lowering the stem. Let's say, for example, that this actuator operates a valve and the valve is closed when air pressure is applied and the stem is down. This design is called air to close, spring to open. If control air is lost, the spring returns the stem to the up position. You'd find this type of setup on a boiler feed water valve, where if you'd lose control air, you'd want the valve to open fully. Single-acting diaphragm actuators are often an important consideration in control system design, since they always return to one position or the other in the absence of a control signal. They can keep a process from running away if something goes wrong in the instrument air system. Single-acting actuators are probably the most common diaphragm actuators found in most plant systems. However, there is another type that you may see in your day-to-day work. It's the double-acting or springless diaphragm actuator. Here's an illustration of one. One big difference is obvious. There's no spring. Instead, the diaphragm and its plates divide the casing into two equal chambers. There are also two ports, one on each side of the diaphragm. Through the ports, air pressure can be applied to either side of the diaphragm. In this illustration, pressure applied here moves the diaphragm and the stem downward. Pressure applied here moves the diaphragm and the stem upward. This is how the double-acting actuator gets its name. Air pressure provides the force for movement in two directions. With no need for a bulky spring, double-acting actuators can be much more compact than single-acting types, an important consideration where space is limited. In most applications, accurate positioning is achieved by keeping one chamber at a constant mid-range pressure. The other chamber receives a varying pressure signal. The difference between the two applied pressures determines the exact position of the diaphragm, the stem, and the control element being operated. Diaphragm actuators, like the types we've just seen, are the most widely used in control systems. There are two main reasons. First, they can be accurately positioned anywhere between their extremes of movement. And second, they're responsive to small variations in control air pressure, making a very sensitive device. Diaphragm types, though, do have one major disadvantage. The total travel of the stem is pretty small. The amount of travel between the extreme positions is limited by the amount of flex of the diaphragm. When more travel is required, there's another type of pneumatic actuator to do the job. Let's see what it looks like. This is a piston actuator. It gets its name from its primary moving part, the piston, which is the component directly acted upon by air pressure. A piston rod connects the piston to the control element being operated. The piston rides inside a cylinder, which is equipped with two ports. Air pressure is supplied to the cylinder or vented from it through the ports. To operate the device, air pressure is applied through one of the ports, while the other port is simultaneously vented to atmosphere. The piston is forced downward. To move in the opposite direction, pressure is applied to this port, while the other is vented. The piston is forced upward. With all the different varieties of pneumatic actuators available, there's a type for almost every application in automatic control systems. On the job, you're sure to encounter several of the types we've seen here. Since pneumatic actuators are so common, we'll be returning to take a closer look at some of the maintenance procedures that apply to them. Before we get to that point, though, take out your textbook and review what we've seen so far about pneumatic actuators. When we return, we'll be applying some of the same principles to a different kind of device, the hydraulic actuator. For truly heavy jobs, where a lot of force is required, remote control of movement depends on having powerful actuators. Hydraulic actuators fill that need. They're powered by liquid pressure, and for their size, they provide more force than any other type of actuator. In this section, we'll look at three common types of hydraulic actuators. We'll see how they're built, and we'll see how they work. This is the simplest kind of hydraulic actuator, single-acting, load return. It has only one moving part, a piston, which is acted upon by a fluid under pressure. The piston rides up and down inside a cylinder. To admit hydraulic fluid, there's a port at the bottom of the cylinder. And to relieve air pressure, there's a vent at the top. The actuator is usually operated by controlling the direction of fluid flow through the port. For example, when liquid under pressure enters the cylinder through the port, it fills the cylinder and forces the piston upward. When the flow stops, the fluid is trapped in the cylinder. It can't escape. Up to this point, the situation is similar to that of a pneumatic cylinder, but here the similarity stops. Liquids are not compressible like air is. When a given volume of liquid is trapped in the cylinder, that volume will not change significantly in spite of any force or weight provided by the load. Once a hydraulic cylinder is positioned, the position won't change. Unless fluid leaks out, downward force will have an insignificant effect on the position of the piston in the cylinder. To move the piston from this position, the direction of flow is reversed. Liquid flows out of the cylinder through the port. The weight of the load pushes the piston back to its original position. At this point, it's easy to see how the single-acting load return actuator gets its name. It's single-acting because fluid pressure acts on only one side of the piston, and it's load return because the weight of the load is the only force acting to return the piston to its original position. We can contrast this design with another type of single-acting hydraulic actuator, the single-acting spring return actuator. This design incorporates a spring in addition to all of the other components common to the load return actuator. Operation of this actuator is identical. Liquid under pressure flows into the cylinder. The piston rod, and load are forced upward, compressing the spring. The difference in this design becomes apparent when the flow of the liquid is reversed. As the liquid flows out of the cylinder, spring tension returns the piston to its original position. Because of the spring, the return action will occur even if the load has been removed from the device. Like other single-acting actuators, the hydraulic actuators we've just seen provide force in one direction only. Hydraulic pressure acts on only one side of the piston. Movement in the opposite direction depends on either the weight of the load or the tension of a spring. In many hydraulic applications, though, it's desirable to operate a cylinder under power in both directions. When that's the case, the solution is a double-acting hydraulic actuator. Let's take a look. Even at first glance, we can easily see two main differences between this double-acting actuator and the single-acting types we looked at earlier. First, the cylinder has two ports. And second, the entire cylinder is filled with hydraulic fluid, not just one side of the piston. When fluid flows into this port, an equal volume is allowed to flow out from the opposite port. When the flow is stopped, the fluid is trapped. The piston can't move in either direction. Reversing the fluid flow moves the piston in the opposite direction. When the flow is stopped, the piston is locked in place by the trapped liquid on either side. Since liquid is incompressible, it doesn't give like compressed air does. Once the actuator is in position, at either extreme or anywhere in between, that's where it's going to stay. On the job, you may have occasion to perform preventive maintenance or repairs to hydraulic actuators. Preventive maintenance often consists of replacing hydraulic fluid or changing the filters that keep it clean. The fluid inevitably picks up some amounts of particles and residue that can foul valves and fittings. Repairs to hydraulic actuators almost always involve leaks, fluid leaks or air leaks. These types of problems are usually remedied by replacing seals, packing, gaskets, or fittings on the unit. Whenever any maintenance is performed on hydraulic equipment, though, keeping air out of the system is essential. Air is compressible, so any air in a hydraulic cylinder will result in mushy control action. If you have to break any couplings or fittings that allow air into the system, the air must be completely bled off before the actuator goes back into service. If you work on hydraulic actuators on your job, you'll find that the material in your text provides a basic background in how they're built and how they work. But for any maintenance to hydraulic actuators, the manufacturer's guidelines should give you the detailed instructions you'll need for both preventive maintenance and for some kinds of repairs. For now, why don't you review the basics in your text? Because when we return, we'll be looking at an entirely different class of devices, electric actuators. For all of the actuators we've seen so far, power has been provided by pressure, either air pressure for pneumatics or liquid pressure for hydraulics. In this section, we're going to take a look at our third major category of actuators, electric actuators. These are devices that provide controlling action using electricity as their power source. Like the other actuators we've seen, electric actuators have important applications in automatic control systems, operating valves, opening and closing dampers, and so on. But as we'll see, electric actuators operate on an entirely different principle. To see just how they work, let's take a look at one common example, a solenoid actuator. This is an example of an actual solenoid actuator that you might see in your plant. The actuator itself is controlled by electric current. Let's look inside. These represent electrical windings. Wire is wound into a coil. When current is passed through the coil, the windings become an electromagnet. In this cutaway view, we can see what the solenoid would look like if it were sliced down the middle. The primary moving part is the armature. The armature is a piece of iron or steel which is attracted to the electromagnetic field when the windings are energized. A stem connects the armature to the device being operated, and a spring holds the armature in its lowered position. To see how it works, let's energize the windings. When current passes through the windings, an electromagnetic field is created. The armature is attracted to the field and is pulled into the center of the coil. The stem lifts to move whatever is connected to it. As you can see, solenoid actuators are necessarily two-position devices. They're either fully extended or fully retracted. There's no in-between position. In practice, the use of solenoid actuators is usually restricted to light-duty applications. Solenoids operate very quickly, but they can't generate a lot of force without being unreasonably large. For applications that do require considerable force and positioning between extremes, another type of electric actuator is typically used, the electric motor actuator. This example shows an electric motor actuator that's used to open and close a door. To see just how it does the job, we'll have to take a look at its arrangement of parts. In principle, the operation of the actuator is fairly straightforward. An electric motor drives a set of gears which in turn open and close the door. To prevent damage to the actuator and the door, two limit switches are provided to control the extreme limits of door travel. When the door reaches its fully open position, this switch opens to cut power to the motor. Likewise, when the door reaches its fully closed position, this switch will open to cut power to the motor. When both limit switches are correctly positioned, they keep the door from exceeding the extreme limits of travel which could damage the actuator. As an instrument technician, you'll often be involved in adjusting limit switches when electric actuators are installed. There are many different types of limit switches and configurations for them. In fact, there are far too many to be discussed here. The important thing to remember is that each limit switch must be set to cut power at exactly the right point of actuator travel. If there's not enough travel, the device will not provide its full controlling action. For example, a door or a valve may not open or close completely. If a limit switch allows too much travel, the device may be damaged by excessive force, or the motor will overheat and burn out. Typically, limits are set by manually operating the device to be controlled and then adjusting each switch so it operates right at the extreme of allowable travel. When you set limits on electric actuators, be sure to refer to the manufacturer's instructions and follow the recommendations for adjustment. There are so many different kinds, that's the only way to be sure of doing the job correctly. On the job, you'll become familiar with the types of electric actuators used at your plant and the adjustments they require for proper operation. For now, though, look through your textbook and review the basic principles we've seen here, the principles of electric actuators. In many industrial processes, pneumatic actuators play an important role in regulating automated processes. As we've seen, pneumatic diaphragm actuators are sensitive to small changes in a control signal and are capable of very precise positioning. For example, this actuator is used to operate a valve. It changes the position of a valve in response to variations in air pressure. The air pressure signal, called control air, is developed by associated parts of a pneumatic control system. Typically, the pressure of control air will vary between 3 and 15 pounds per square inch. However, the manufacturer states that this actuator needs a pressure of 35 psi to fully open the valve. Obviously, control air pressure alone isn't sufficient to open the valve. To operate the actuator and its valve, we need a way to multiply the force of the control air signal. In this situation, we rely on a positioner. This positioner is only one of many different designs. All positioners, though, operate on the same general principle. They use a small pressure to control a larger pressure. In this example, the positioner has 3 pneumatic lines connected to it. This line supplies the positioner with a constant 40 psi of air pressure. The positioner regulates this pressure and produces an output that is supplied to the actuator through this line. This third line supplies the positioner with control air that varies between 3 and 15 psi to operate the positioner. 3 pounds of control air to the positioner produces 0 pounds of output to the actuator. 15 pounds of control air to the positioner produces 35 pounds output to the actuator. At every value in between, the output will be proportional to the input. To see just how a typical positioner does the job, let's take a look at a simplified version of this device. The easiest way to understand positioner operation is to look at the device a piece at a time. We're going to deal with this one in terms of 3 functional blocks: input, output, and feedback. We'll start at the beginning, the input. In this version, the input block consists of an inlet for control air and a bellows. When control air pressure increases, the bellows expands. Likewise, when control air pressure decreases, the bellows contracts. As the bellows moves, its motion is transferred to the output section by a pivoting arm called a force beam. The tip of the force beam moves up and down in direct relation to any change in control air pressure. This motion regulates the output section. In this example, the output section is composed of 3 components. It has a supply port, which receives the constant 40 psi air supply, and it has an output port. From here, the regulated pressure leaves the positioner and goes to the actuator. The third component is the pilot valve assembly. There's a valve body and a stem. The stem is attached to the tip of the force beam. So as the force beam moves, the stem of the pilot valve moves with it. The position of the stem controls the output port's airway. When the stem rises, air flows from the supply to the output. Output pressure increases, increasing the pressure on the actuator diaphragm. When the stem is partially lowered, it blocks the output and holds the output pressure at a fixed value. This pressure is trapped in the actuator and keeps the diaphragm at a fixed position. When the stem is lowered fully, the air supply is closed off, and the output port is opened again. But this time, the trapped pressure is released. Air is vented through the top of the pilot valve, relieving the pressure on the actuator, which returns to its original position. By precise control of pilot valve position, we can accurately regulate the pressure and control the position of an actuator. When a control air pressure is applied to the input, the bellows expands and moves the force beam up. The pilot valve opens to admit air to the actuator. But when the desired pressure to the actuator is reached, the pilot valve must be closed. The feedback section serves that function. The feedback section consists of a feedback link, a cam, a range lever, and a spring. The feedback link is directly connected to the actuator stem. As the actuator lifts, so does the feedback link. Moving the feedback link rotates the cam, which depresses the range lever and stretches the spring. The spring tension pulls down on the force beam, closing the pilot valve when the actuator is in a position that is proportional to the input signal. The exact position of the pilot valve then depends on a balance of two forces, the upward force of the bellows and the downward force of the spring. For every input pressure, there's a corresponding position of the feedback link that will cause the pilot valve to close. When the positioner is properly adjusted, the resulting output pressure is directly proportional to the input pressure. The feedback section determines when the actuator is in the correct position and closes the pilot valve to shut off the flow of air. Pressure is trapped in the actuator, holding it in a fixed position. To complete the general overview of positioner operation, let's see what happens when control air pressure is decreased. When bellows pressure is reduced, spring tension pulls the force beam downward. The pilot valve stem moves downward and vents the actuator's pressure to the atmosphere. As the actuator moves toward a new position, the feedback section decreases tension on the spring. When the new actuator position is reached, the force of the spring once again exactly balances the force of the bellows. The pilot valve closes, trapping the remaining pressure and holding the actuator in its new position. In this general overview of positioner operation, we've seen the basic components of a typical positioner and how they work together to convert small variations in control air pressure into proportionally larger variations in output air pressure. In this brief discussion, we've investigated the general principles of how positioners do their job. But, as you'll discover, there are many exceptions to the typical setup we've just seen. As you continue your study of instrumentation and control, you'll learn more about positioners and their maintenance. For now, though, read your textbook to review their general operation. When we return, we'll finish off this unit with a look at some maintenance procedures that you're likely to do on pneumatic actuators. Up to this point in our study of actuators, we've been primarily interested in general principles. We've learned how they work, so now we're ready to see how they're maintained. In this section, we're going to take a look at some maintenance procedures for pneumatic actuators. In these examples, we'll see both a diaphragm type and a piston type. We're going to start with this diaphragm actuator. It's a single-acting type that operates a valve. When there's no air pressure on the actuator, the valve is closed. And when 35 pounds of air pressure is applied, the valve opens fully. The routine maintenance procedure we're about to see involves disassembling the actuator, inspecting its parts, and replacing the diaphragm. And as we'll see, the actuator will also require a simple adjustment, so it'll position the valve correctly at each point along its pressure range. Let's start then by going to the shop for the first part of the maintenance procedure, disassembly. On any single-acting diaphragm actuator, the first step in the disassembly procedure is releasing tension on the return spring. On this actuator, spring tension is released by loosening this nut on the actuator stem. This step removes all pressure on the diaphragm. If spring tension is not removed, it could cause the internal parts to fly apart as disassembly continues. When the nut's completely loosened and there's no tension on the spring, the casing bolts can be removed. When they're all out of the way, the casing can be removed, revealing the internal parts of the diaphragm assembly. On this actuator, a retaining bolt and a spacer secure the diaphragm and its plate to the actuator stem. The bolt and spacer must both be removed to free the diaphragm for removal. Once they're out of the way, the diaphragm plate is lifted out, and the diaphragm is pulled from the casing. Before a new diaphragm is installed, it's a good idea to wipe off the top of the stem and the lower casing. All areas that come in contact with the diaphragm should be inspected for any rough areas that could damage the diaphragm. The diaphragm plate also has to be clean and smooth. If any rough edges were apparent, they'd be smoothed out with fine-grade emery paper. Once everything's been cleaned and inspected, a new diaphragm can be installed. The diaphragm plate goes into position next. Then the spacer and retaining bolt are screwed into the stem to hold everything in place. Once the retaining bolt is finger tight, it's fully tightened with a wrench. Unless it's tightened all the way, free play will result in inaccurate positioning when the actuators return to service. And if it came loose, the actuator wouldn't move the valve. Like all of the other parts, the top half of the casing should also be clean before being replaced. Again, after wiping it off, the technician feels for any sharp or rough areas which could damage the diaphragm. If everything's okay, the upper casing can be installed. After a check to make sure the bolt holes in the diaphragm line up with those in the casing, the upper casing is placed in position and its bolts are replaced. Once all of the bolts are in place and the casing has been evenly tightened, reassembly is complete. The next step is adjusting spring tension to ensure that the position of the actuator will be correct for every input pressure within its range. To make the adjustment easy to do, it's a good idea to lubricate the threads on the actuator stem. Then the spring tension adjustment nut is partially tightened, so it begins to put some tension on the spring. To make the final adjustment, air pressure will be applied to the actuator and compared to stem travel. For right now, a rough estimate is made. The nut is tightened to an approximate position. Once an approximate adjustment has been made, the actuator is connected to a source of instrument air. Before making any final adjustments, the technician tests for air leaks. To do this, he applies full operating pressure to the actuator, which in this case is 35 psi. Then he squirts a leak detector on areas of the actuator where leaks may occur. If a leak is present, the leak detector will bubble. He also checks the vent on the top of the actuator for leaks. By putting his finger over the vent, he can feel for a buildup of air pressure, which would indicate a leak in the diaphragm assembly. There aren't any leaks, and so the technician can proceed with the final adjustment. Basically, he'll be adjusting the spring tension, so when a given pressure is applied, the actuator stem travels a specified distance. The amount of travel is determined by looking at this position indicator plate next to the stem. The position of this disc on the stem, in relation to the scale, indicates the position of the valve. At 0 psi, the valve should be fully closed. At 35 psi, the valve should be fully open. For our demonstration, the technician will be adjusting this extreme. However, the procedure for adjusting the actuators in your plant may be different, and so make sure to refer to your plant's procedures or the manufacturer's instructions. The final adjustment begins by slowly applying air pressure to the actuator. As he applies the pressure, he watches the position indicator on the actuator. When the indicator on the stem has moved to the fully open position, the technician looks at the air pressure gauge again. The gauge indicates 30 psi. That's a little low. The valve should be fully open at 35 psi. So the technician will have to adjust the nut to increase spring tension. When he feels that he has tightened it sufficiently, he'll test it again to see if he's close. Once the spring tension has been changed, he applies air pressure and allows the indicator on the stem to move to the fully open position. This time, the air pressure gauge indicates 35 psi. That's the desired air pressure at which the valve on this particular pneumatic actuator is supposed to be fully open. As a result of his experience, and because he was lucky, he was able to adjust it to the desired spring tension on his second try. Usually it requires a number of attempts before the correct spring tension is achieved. The actuator has been correctly adjusted and can now be returned to service. The example we've just seen is a fairly common maintenance procedure wherever pneumatic diaphragm actuators are used. Rubber parts have to be replaced because they wear out, and basic adjustments are almost always required after reassembly. Our next maintenance example involves a pneumatic piston actuator. This actuator could be used to position a damper or in other applications where a long travel is needed. This is the actuator's feedback spring. As you may recall from the last segment, the feedback spring is part of the actuator's positioner. This portion of the unit is its positioner. This is a fairly typical setup for pneumatic piston actuators. So let's go to the shop and see just what kind of maintenance these devices need. Once again, the basic procedure involves disassembly, inspection, and replacement of parts. The first step is disconnecting the air line that connects the pneumatic cylinder to the positioner. For work on the actuator itself, the positioner must be removed completely. The feedback spring is detached. The bottom plate of the positioner is pulled off. And then the positioner housing is unbolted and removed from the cylinder. Now the cylinder itself can be disassembled for inspection. First, one end cap is removed, and the piston rod is pulled to the fully extended position. The cylinder can now be removed, exposing the internal parts. Periodically, these cups have to be replaced because they wear or become brittle with age. To remove the cups, the entire piston is disassembled as each of the parts is pulled off of the piston rod. It's placed in a tray for cleaning. Only the metal parts will be cleaned. The cups are removed from their retainers and discarded. non-flammable, non-toxic solvent is used to clean the metal parts. Because almost all solvents give off harmful vapor, adequate ventilation of the work area is essential during this part of the job. Rubber gloves are also helpful because most solvents are also irritating to the skin. A good brushing should remove all of the built-up grease and dirt on the parts. Once everything's been cleaned, the parts are inspected prior to reassembly. The cylinder bore should be smooth, with no signs of scoring or other damage. The piston rod must also be in good condition. If there are any rough spots or rust on the rod, sometimes a light sanding is all it takes to smooth away the imperfection. Once all the parts have been inspected, reassembly can begin. New cups are placed on their retainers. The new cups will form a positive seal between the piston and the cylinder walls. Reassembly of the actuator is merely the reverse of the disassembly procedure. First, one of the end caps slides onto the piston rod and is placed in position. Then the piston assembly goes back on. The piston assembly is greased with the lubricant recommended by the manufacturer. This helps form a positive airtight seal between the piston and the cylinder bore. The inside of the cylinder also gets a coating of the same lubricant. In addition to its sealing properties, the lubricant reduces friction inside the cylinder, allowing the piston to travel with a minimum of resistance. An even coating over the entire bore also helps prevent corrosion of the metal. Once lubrication is complete, sealant is applied to the end caps. The end caps have to be airtight, so no air leaks out of the cylinder when pressure is applied during operation. At this point, the rest of the actuator parts can go back into place. The cylinder slides on over the piston. Once it's in place, the opposite end cap can go on, and the cylinder can be bolted together. Once the actuator is completely reassembled, the positioner is replaced and its air line is connected. This end cap is equipped with a grease fitting, so before testing the actuator for proper operation, the technician greases the unit according to the manufacturer's recommendations. Now only one more reassembly step remains, attaching the feedback spring. Once the piston rod is fully retracted, the spring can be connected easily. Now the actuator is connected to instrument air. Testing the device for proper operation under pressure is the only way to really check the effectiveness of the repair. Let's see what happens when pressure is applied. The actuator moves, just as it's supposed to. This particular actuator is designed to operate at either its fully extended or fully retracted positions, not in between. No precise adjustments are necessary, as long as the actuator will fully extend at its rated pressure and fully retract when pressure is removed. Since everything seems to work, the only remaining task is to check for leaks. All of the fittings are squirted with leak detector. Any bubbles would indicate air leaks, which would have to be repaired before putting the actuator back into service. The end cap joints are also tested. No leaks are detected, so this actuator is ready to go back in place. In this unit, we've covered everything from basic principles to common maintenance procedures for actuators. As we've seen, actuators come in a variety of shapes, sizes, and designs. They can use either electricity, liquid pressure, or air pressure for their force. In your job, you're likely to be working on actuators fairly often, and as you continue your study of instrumentation maintenance, you'll learn more about pneumatic actuators, the most common of the types we've seen here. At this point, though, you should have a good grasp of the basics, the fundamentals of actuators, positioners, and actuator maintenance.